Good day to all of you. So we're already on chapter 12 of operating systems course, which is all about I/O systems or input and output systems. So what are these I/O systems? So if you really want to know what is I/O systems, so let's start our lesson. So again, chapter 12 is all about I/O systems. So the contents of this chapter are, we have the overview, we have the I/O hardware, application I/O interface, kernel I/O subsystem, transforming I/O requests to hardware operations, streams, and last but not the least is we have performance. So the objectives of this chapter are explore the structure of an operating system's I/O subsystem, discuss the principles and complexities of I/O hardware, and explain the performance aspects of I/O hardware and software. So for the overview, so I/O management is a major component of operating system design and operation. So it is an important aspect of computer operation, and because of that, I/O devices vary greatly. So what are this some of the examples of I/O devices? Of course, we have the keyboard, the mouse, the monitor. So our flash drives, these are also considered as I/O devices. And other devices that can be connected to our computer or to our personal computers, they are considered also as I/O devices. So that's why, as it is said, that I/O devices vary greatly. Then it has various methods to control them, of course. Since it's a keyboard, it has a different device driver for mouse, for monitor. And then next is we have the performance management and the new types of devices frequent. As I've said, because of technology, there are devices that can be connected to our computer that is newly innovated or newly invented. So because of the innovations, we have new types of devices that is produced or that is of course invented nowadays. And then ports, buses, device controllers connect to various devices. And then device drivers encapsulate device details. As I've said from our previous lessons, that device drivers acts as the identification or ID of our hardware, of our I/O devices. And then present a uniform device access interface to I/O subsystem. As I've already cited in our previous lesson, for example, you have a flash drive or thumb drive. Of course, it's a different brand. So even though it's you installed or you inserted, connected a USB flash drive into your computer with different brands, for the computer, they will always be identified as a USB device or to be specific, a flash drive. Okay, next is we have the I/O hardware. So incredible variety of I/O devices. So they can be roughly identified or categorized as storage, as you can see with our USB flash drives. It can also be used for transmissions. For example, you have a Bluetooth dongle if your personal computer does not have a Bluetooth radio device that is included. Almost all of the laptops have Bluetooth, and personal computers or the typical desktop computers does not have a Bluetooth, so you need a Bluetooth dongle. So that's an example for transmission. And of course, we have human interface such as, of course, mouse, we have keyboards, and then we also have drawing pads. So that's also included with human interface. So common concepts. So signals from I/O devices interface with computer. So this interfaces is we have the port, connection point for the device, and then it can also be connected through bus. So by daisy chain or shared direct access, I already discussed how is daisy chain done. So PCI bus, common in PCs and servers, and we have another one, the PCI Express, the more improved version of PCI. And then we have expansion bus connects relatively slow devices. So expansion bus, so this what devices are connected in the expansion bus? So we have the keyboard, serial, and USB ports. And then we have the serial attached SCSI or SAS. I've already also discussed SCSI in our previous chapters. So it is common for disk interface. And then we have a controller, or another term for controller is the host adapter, electronics that operate the port, bus, and the device. Sometimes the controller is integrated, meaning if you already bought a motherboard, it is already there in the motherboard. It's already integrated. Sometimes it is a separate circuit board, or it is called the host adapter rather. And then it also contains processor, microcode, private memory, bus controllers, and others. So some talk to per device controller with bus controller, microcode, memory, and others. So this is the typical PC bus structure. So for this example, all of the controllers are connected with PCIe bus, the PCI Express bus. So for example, our monitor is connected to the PCIe bus by means of a graphics controller, and then the processor, the cache and memory, it is connected through the bridge or memory controller. And then for the disk, we have the SAS controller, SAS controller. And then for our expansion bus interface, as I've said, expansion bus, it is where the keyboard, serial, and USB ports are connected. So from this interface, keyboards and other USB ports are also connected by using the expansion bus. So this is the typical PC bus structure. So continuation for the I/O hardware. So fiber channel, as I've already discussed again in the previous chapters, or the FC, is a complex controller, usually separate circuit board, or a host bus adapter, or HBA, plugging into bus. And then I/O instructions control devices. And then devices usually have registers where device driver places commands, addresses, and data to write or read data from registers after command execution. So these devices have registers where the device driver communicates by means of the commands, addresses, and data to write or read data. And then we have the data. What are these registers? We have the data in register, the data out register, the status register, and the control register. So typically 1 to 4 bytes, and it has a FIFO buffer, or first in, first out buffer. And devices have addresses, which is used by direct I/O instructions, or it can be used by memory mapped I/O. So what is a memory mapped I/O? So device data and command registers map to processor address space, and especially for large address spaces, such as, of course, since for graphics it uses a huge amount of data, so they are using memory mapped I/O. Okay, we have the device I/O port locations on PC. So this is a partial list. So these are the I/O address range in hexadecimal. So for this range, we have the DMA controller. So we have also for the interrupt controller, the timer, game controller, serial port for the secondary, and then hard disk controller, parallel port, graphics controller, diskette drive controller, and serial port for primary use. So these are the port locations that is used by devices. So these devices will be categorized depending on their where this will be connected. Okay, next is we have polling. So for each byte of I/O, read busy bit from status register until 0. And the number 2, host sets read or write bit, and if write, copies data into data out register. And the next is host sets command ready bit. And then number 4, controller sets a busy bit, executes transfer. And then controller clears busy bit, error bit, command ready bit when transfer done. So step 1 is busy wait cycle, to wait for I/O from device. So again, the word busy wait, as already again, in reference with the previous chapters is busy wait is if you're not it's not yet your turn, so every time there's maybe an interval, you're going to check if it is already available. So that is busy wait. It's like the example as if you can remember, for example, in a real world situation, somewhere someone is inside the comfort room and it's your turn next to use it, and then since there's still person inside, you will go back, for example, to your workplace, and then you're going to check again if it's already free. So that is what we call busy waiting. So for step one, so reasonable if device is fast, but inefficient if device is slow. So what if, to compensate for that, CPU switches to other tasks? The problem with that is that, but if the CPU misses a cycle, data can be overwritten or lost. Okay, let's continue. So we have interrupts. So polling can happen in three instruction cycles. So these three instruction cycles are read status, logical and to extract status bit, and branch if not zero. So how to be more efficient if non-zero infrequently? So arrange for the hardware controller to notify the CPU when the device becomes ready for service rather than to require the CPU to poll repeatedly for an I/O completion. So by means of that, you going to use the interrupts. So CPU interrupt request line triggered by I/O device, checked by processor after each instruction, and then the interrupt handler receives interrupts, of course. And then maskable to ignore or delay some interrupts. So meaning of maskable, you can ignore the interrupts if it does not have a higher priority. So interrupt vector to dispatch interrupt to correct handler. So what happens is that context switch at start and end, and it is also based on priority. Some are non-maskable. So non-maskable means you cannot ignore that interrupt. You have to service it first. And then interrupt chaining if more than one device at same interrupt number. So you already has seen this from the previous chapters, the interrupt driven I/O cycle. So again, for number one, so this is the CPU. So this is the activity of CPU. So number one is device driver initiates I/O. Then number two, so from the I/O controller, so initiates I/O. And then number three, input is ready, output complete, or error generates interrupt signal. And then number four, so between 1 and 4 is we have CPU executing checks for interrupts between instructions. And then next is we have CPU receiving interrupt, transfers control to interrupt handler. And then we have number 5, interrupt handler processes data, returns from interrupt. And then next is number 6, CPU resumes processing of interrupted task. And then again, it will wait again if the device driver initiates I/O. So that is what is happening with interrupt driven I/O. So if the CPU is busy and then it receives initiation from the I/O, it has an initialization, and then the CPU will stop what is executing and it has to service first because of the interrupt. So the continuation again is the interrupt mechanism is also used for exceptions. So examples of exceptions are terminating a process, crash system due to hardware error. And then also page fault executes when memory access error. Then system call executes via trap to trigger kernel to execute request. Multi-CPU systems can process interrupts concurrently. So of course, because it has two or more central processing unit or microprocessor, that it can process interrupts concurrently or simultaneously. So if operating system is designed to handle it, of course, you have a multi-CPU system, but what if your operating system is not designed for processing interrupts concurrently or simultaneously? So your multi-CPU system will not work. It depends also with your operating system. And then this is also used for time-sensitive processing, frequent, and must be fast. So next is we have latency. So stressing interrupt management because even single user systems manage hundreds of interrupts per second and serves hundreds of thousands. So for example, so we have this snapshot. So for a quiet Mac OS desktop, it generates 23,000 interrupts over 10 seconds. So that is how a computer handles interrupts, as many as 23,000 interrupts over 10 seconds. So it means that for every 1 second, um, the interrupt that is generated is 2,300. Okay, next is we have the Intel Pentium processor event vector table. So this is for the interrupt. So for vector number 0, this is divide error. And then, of course, there's for debug exception, null interrupt, breakpoint, into detected overflow, bound range exception, invalid opcode, device not available, double fault, coprocessor segment overrun, and then invalid task state segment, segment not present, stack fault, general protection page fault. So vector number 15 is Intel reserve. It is not used. And then 16 is floating point error. 17 is alignment check. 18 is machine check. And then from 19 to 31, again, it is used by Intel and it cannot be used any other than what is Intel has a purpose for that. And then from 32 to 255, these are maskable interrupts. Again, as I've said with the term maskable, meaning this can be ignored if there are other interrupts which has higher priority from compared to 32 vector number 32 to 255. So such as this, for example, vector number 0, this is the divide error. So this will be serviced first. Okay, next is we have direct memory access. So used to avoid programmed I/O or 1 byte at a time for large data movement. So it requires a DMA controller. By means of DMA, it bypasses CPU to transfer directly between I/O device and memory. So the OS writes DMA command block into memory. So what is this block? What is the composition of this block? Is we have the source and destination addresses, read or write mode, count of bytes, writes location of command block to DMA controller, bus mastering of DMA controller, grabs bus from the CPU. So we have this term cycle stealing from CPU, but still much more efficient. So what do you mean by cycle stealing? Since DMA, of course, that's why it's called direct memory access, instead of the I/O device will still the CPU is in the middle of the memory and I/O device. The memory has a direct access with the I/O device without CPU intervention. So cycle stealing, since the CPU is the one who's almost using the bus for execution and transfer of data. So by means of DMA, it can borrow or it can accommodate the bus exclusively. So it's like CPU will give way once the DMA controller or the wants to use the bus. So when done, interrupts to signal completion. So version that is aware of virtual addresses can be more efficient. So we have the DVMA or the direct virtual memory access. So this is the actually, it is written as 6 step, but actually, as you can see, it is only 5 step. So, process to perform DMA transfer. So, step number 1. So, device driver is told to transfer drive 2 data, which is this one, to buffer at address X. So, you have to transfer this data to this address. And then number 2, Device driver tells drive controller to transfer C bytes to buffer at address X. So we have the controller. So the SAS drive controllers is informed that this should be transferred C bytes. The capacity or the how large the data to be transferred to this address. And then number 3, drive controller initiates DMA transfer. So instead, of course, of going with the CPU without CPU intervention, it can directly access, or it has a feature for DMA transfer. And then number 4, the DMA controller transfers bytes to buffer X, increasing memory address and decreasing C until C is equal to 0. And then number 5, when it is already transferred from drive 2 to the memory, so when C is equal to 0, DMA interrupts CPU to signal transfer completion, so that again, that the CPU can use again the bus. So for this illustration, so when the entire transmission is finished, the DMA controller interrupts the CPU. When DMA controller seizes the memory bus, the CPU is momentarily prevented from accessing main memory, though it can still access data items in its caches. Although this cycle stealing, as of previous slide, can slow down the CPU computation, offloading the data transfer work to a DMA controller generally improves the total system performance. So that's the explanation why DMA is included, because though it still cycles from CPU, but it has an improvement with the overall performance of the system. Okay, next is we have application I/O interface. So I/O system calls encapsulate device behaviors in generic classes. Then the device layer hides differences among I/O controllers from kernel. So as I've said again, so if it is a flash drive with different brands, but still it's classified as a flash drive. And then new devices talking already implemented protocols need no extra work. And then each OS has its own I/O subsystem structures and device driver frameworks. And then devices vary in many dimensions. So these are the roughly classification. We have character stream or block. This is for data transfer mode. And then sequential or random access. This is the access method for I/O devices. Next is we have synchronous or asynchronous or both. This is for the transfer schedule. Shareable or dedicated, it is for sharing. And then speed of operation is for the device speed. And read-write, read-only, or write-only, this is for the I/O direction. So this is the kernel I/O structure. So we have the kernel, and then we have the kernel I/O subsystem, and then it has a device driver for SAS, for keyboard, for mouse, and then for any other I/O devices. We have for PCI bus device driver. So this is for wireless connections 802.11, and then we have USB device driver. So the kernel, a kernel I/O subsystem, and the device driver that is enumerated or included, these are all software. And then for hardware, so this SAS device controller, it has a the device driver has a corresponding controller. So these are all in the motherboard, or of course if it is a separate circuit board. It depends upon the setup of your computer system. And then connected to device controllers are the different SAS devices. Of course, for keyboard, device controller is a keyboard, and mouse is for mouse, of course. And then for PCIe bus device controller, any devices that can be connected using PCIe. And then for 802.11 device controller, so any wireless connection devices. And then for USB device controller, any devices that has a USB interface. Okay, so next is we have a table of the characteristics of I/O devices. I've already mentioned it in the previous slide. So again, For data transfer mode, so for character, it is a terminal. Terminal is the like the MS-DOS. So you have to type the commands. And then for block, so we have disk. And then for access method, sequential. So sequential modem uses sequential access method. And then for random, for examples, we have the CD-ROM. Then for transfer schedule, for synchronous, we have the tape. And then asynchronous, we have the keyboard. I already explained why it is asynchronous because it follows whatever the user has to type. It does not have any sequence, or it does not follow a time in which the letter will appear on the screen. And then next is we have the sharing. So for dedicated, again, it's for the tape, and shareable is for the keyboard. And then device speed is we have latency, seek time, transfer rate, delay between operations. And then we have I/O direction. For read only is we have the CD-ROM. And then we have write only graphics controller. And then we have the read write, we have disk. Okay, next, let's continue. So again, characteristics of I/O devices. So subtleties of devices handled by device drivers. So broadly, I/O devices can be grouped by the OS into block I/O, character I/O or stream, memory map, file access, and network sockets. So for direct manipulation of I/O device specific characteristics, usually an escape or backdoor is used. So what is this escape or backdoor? Transparently passes arbitrary commands from an application to a device driver. So UNIX IOCTL system call to send arbitrary bits to a device control register and data to device data register. So Unix and Linux use tuple of major and minor device numbers to identify type and instance of devices. So here, major is 8 and minors is from 0 to 4. So this is the command for the Unix and Linux. So next is we have block and character devices. So block devices include disk drives as already mentioned. So commands include read, write, seek. So we have raw I/O, direct I/O or file system access. So for raw I/O, direct access to a secondary storage device as an array of blocks with no file system. So that is why it's called raw I/O. And then for the direct I/O, so block I/O that bypasses operating system block features such as buffering and locking. So next is we have memory mapped file access possible. So file mapped to virtual memory and clusters brought via divan paging. So it also has this DMA or direct memory access. And then character devices includes, of course, as we have mentioned, keyboards, mice, and serial ports. So commands include get and put system call, and then libraries layered on top allow line editing. So next is we have network devices. So varying enough from block and character to have own interface. So Linux, Unix, Windows, and many others include socket interface. So socket is an interface for network I/O. So it separates network protocol from network operation, and it includes the select function functionality. So approaches vary widely. So for network devices, we have pipes, FIFOs, streams, queues, and mailboxes. Next is we have clocks and timers. So for this, so provide current time, elapsed time, and timer. Normal resolution is about 1 over 60 second. And then some systems provide higher resolution timers. And then we have programmable interval timer. This is used for timings, periodic interrupts. So the IOCTL on Unix, of course, is specific for Unix, covers odd aspects of I/O such as clocks and timers. So next is we have non-blocking and asynchronous I/O. So blocking as definition is process suspended until I/O completed. So blocking, it is easy to use and understand. And it is insufficient for some needs. Why? Because blocking is insufficient because physical actions performed by I/O devices are generally asynchronous. And then we also have another one, the non-blocking. The I/O call returns as much as available. So it uses a user interface and data copy or buffered I/O implemented via multi-threading, returns quickly with count of bytes read or written, and then select function to find data to find if data is ready, then read or write to transfer. And another one is we have the asynchronous process runs while I/O executes. So this is the opposite of blocking. So blocking process suspended until I/O completed. For asynchronous, even though the I/O is in execution, the process will still run. So for asynchronous, of course, it is difficult to use, and then I/O subsystem signals process when I/O completed. So this is an illustration of two methods. We have synchronous and asynchronous. So for the user, so there's a process that will request, then it goes to the device driver, and then we have for the hardware, and then there is this data transfer. So it means for synchronous, it has a time interval before it will return to the process which is requesting for a service. While we have the synchronous, so as long as the transfer is finished, it can return anytime with the requesting process without any it does not follow any sequence or time intervals for it to service the request. Okay, next is we have the vectored I/O. So vectored I/O allows one system call to perform multiple I/O operations. So for example, UNIX read VE function accepts a vector of multiple buffers to read into or write from. So this scatter-gather method better than multiple individual I/O calls. So this decreases context switching, that's the advantage, and system call overhead. And then some versions provide atomicity. So atomicity is assuring that all the I/O is done without interruption. Avoid, for example, worry about multiple threads changing data as read or writes occurring. Okay, next is we have the kernel I/O subsystem. So it has a scheduling. So some I/O requests ordering via per device queue. Then some OSS try fairness. And then some implement quality of service such as IP QoS or Internet Protocol Quality of Service. So what is that? So manage traffic to avoid network congestion. And then next is we have buffering. So store data in memory while transferring between devices. So buffering is done. It is because to cope with device speed mismatch, to cope with device transfer size mismatch, and then also to maintain copy semantics. So copy semantics is the right way to preserve control over object ownership. And then for buffering, it can all double buffering can also be implemented. So two copies of the data. So it can be used in kernel and user mode. It has varying sizes, can be full or being processed and not full or being used. So copy on write can be used for efficiency in some cases. So copy on write is already discussed in the previous chapters. So we have an illustration here of a device status table. So as you can see, we have, in this example, we have a device such as, let's return, we have keyboard, laser printer, mouse, disk unit 1, and disk unit 2. We have ellipsis here, meaning there are other devices that is connected. So for just illustration, it's shown only a partial list of devices. So keyboard, mouse, and disk unit 1, these are all idle because there are no requests for this hardware devices. And then for laser printer, it is busy because it has a request for the laser printer while the disk unit 2 is also busy because it has two requests. So that is how the device status table works. For this example, this we have two requests. So it is in queue, in first out order. Okay, next is we have the common PC and data center I/O devices and interface speeds. As you can see, the slowest, of course, is the keyboard, and the fastest is the PCI Express third generation. Okay, you see the speed for in gigabytes per second. Okay, next is we have the kernel I/O subsystem. So it has caching, just a feature of caching, faster device holding copy of data. So always just a copy. It is also a key to performance. I've already discussed the caching by means of the memory hierarchy. And then it's also sometimes combined with buffering. So next is we have spooling. So hold output for a device. So if device can serve only one request at a time, so spooling is mostly is happening with the printers. They're using these spoolers. And then next is we have device reservation. So provides exclusive access to a device. So that's why it's like device the this type of device is reserved for a particular um, process. So system calls for allocation and the allocation, and of course, because of devices reserved for a particular process, so watch out for deadlock. So let's return with this spooling. So for printers, for example, if you're going to print something, you have three computers. It is connected through a printer on through a network. And then what if you have an experiment that you want to print, who's going to print first? You hit the print button all at the same time. Which of them will be printed? Actually, it depends upon which of them is the fastest. But don't worry, you can already close your application. Even the application once you've already sent the command to print this document. Because others the others thought that, for example, you're printing a document in a word processor. You need to finish first the printing before you close the your document. No, for printing, it does not really necessary for you to wait or close the for you to wait for the printer to finish and then close your your file. So that is what we call spooling. It's like the printer has its own memory in which it can arrange, or it can service the requests of a particular computer that wants the service of a printer. Okay, next is we have the error handling. So OS can recover from disk read, device unavailable, transient write failures. So for this one, retry a read or write, for example, and then some systems are more advanced. So for Solaris, FMA, or the fault management architecture, and then we also have AIX, is we have the Advanced Interactive Executive by IBM. So what are these characteristics of this advanced error handling? Track error frequencies. Stop using device with increasing frequency of retriable errors. So most return an error number or code when I/O request fails, so to notify the user. And then system error logs hold problem reports. Okay, next is we have I/O protection. So user process may accidentally or purposefully attempt to disrupt normal operation via illegal I/O instructions. So all I/O instructions defined to be privileged, and then I/O must be performed via system call. So that's why that is one way of I/O protection. So memory mapped and I/O port memory locations must be protected too. Okay, next is this is an example, an illustration of a use of a system call to perform I/O. So we have number one is trap to kernel, and then if there's a trap to kernel, there's a corresponding system call, which is, for example, it's called N, and then it will from the user mode it will go to the kernel mode, and then system call dispatch to N, and then what if whatever is the system call is that, and then it will read here. So that's why number two is perform IO. And then next is number three, return to calling thread. The thread that is requesting for that particular service of the IO. Okay, next is we have kernel data structures. So the kernel keeps state information for I/O components, including open file tables, network connections, and character device state. So many complex data structures to track buffers, memory allocation, and dirty blocks or the modified blocks. And then some use object-oriented methods and message passing to implement I/O. So Windows uses message passing. So message with I/O information passed from user mode into kernel. Then message is modified as it flows through to device driver and back to process. What are the pros and cons of this message passing? So it can add overhead by comparison with procedural techniques that use shared data structures, but it simplifies the structure and design of the I/O system and adds flexibility. Okay, next is we have for this illustration is we have a UNIX I/O kernel structure. So this open file record contains a dispatch table that holds the pointers to the appropriate routines depending on the type of file. So for example, in the user process memory, for the per process open file table, this contains a file system record and a networking socket record, and then so this will be in the kernel memory, and it is inside the active inode table for the file system record, and then the network or socket record is in the network information table. So next is we have power management. So not strictly domain of I/O, but much is I/O related. Why? Because computers and devices use electricity, generate heat, frequently require cooling. So OSS can help manage and improve use. So cloud computing environments move virtual machines between servers, and then can end up evacuating whole systems and shutting them down, because cloud computing environments, in terms of cost, it is less costly because it does not, the company that will require the service of cloud computing will require less hardware such as server to put the data. So instead, it will be hosted from a cloud. So of course, with regards to the cost, it will be lesser. You're only going to pay for the service of the cloud, and of course the servers that will be used. And then mobile computing has power management as first class OS aspect. So for example, so for the mobile, Android implements component level power management. So how it is done? So understand relationship between components, build device tree representing physical device topology. So for Android, system bus, then I/O subsystem, and then flash or USB storage. And then device driver tracks state of device, whether in use, and then any unused components will be turned off, and then all devices in tree branch unused is, yeah, the Android will turn off that branch. And then it also implements wake locks like other locks, but prevents sleep of device when lock is held. And then it also has power collapse, put a device into very deep sleep. So if it's already in the very deep sleep, it has a marginal power use, then only awake enough to respond to external stimuli such as button press or incoming call. So modern systems use advanced configuration and power interface or ACPI firmware, providing code that runs as routines called by kernel for device discovery, management, error, and power management. So most of the computers and specifically laptops, they are using this ACPI. Okay, so the kernel I/O subsystem summary. So in summary, the I/O subsystem coordinates an extensive collection of services that are available to applications and to other parts of the kernel. So these are the services, at least. So management of the namespace for files and devices, access control to files and devices, operation control, for example, a modem cannot seek, and then file system space allocation, device allocation, buffering, caching, and spooling. We have I/O scheduling, device status monitoring, error handling, and failure recovery, device driver configuration, initialization, and power management of I/O devices. So the upper levels of the I/O subsystem access devices via the uniform interface provided by the device drivers. So next is we have transforming I/O requests to hardware operations. So consider reading a file from disk for a process. So determine device holding the file, translate name to device representation, physically read data from disk into buffer, make data available to requesting process, and return control to process. So we have a life cycle of an I/O request. So again, in the user mode, we have a request I/O. And then for a request I/O, there is a corresponding system call. So it is already inside the kernel. So we have a decision here from the in the kernel I/O subsystem can already satisfy I/O request. If it is a yes, so it will place data in return values or in process space and then return from system call, and then I/O complete, input data available, or output is already completed. What if the answer is no? For the question can already satisfy I/O request. So next is send request to the device driver block process if appropriate. So it will go to the device driver. So we're already here in the device driver. So process request, issues commands to controller, configure controller to block until interrupt. And then next, it will go to the device controller. So execute command and monitor device. Then next is IO complete, generate an interrupt, and then from the interrupt handler, receive interrupt, store data in device driver buffer. If input, then signal to unblock device driver. So in the device driver, because it is passed, determine which IO is completed, indicate state changes to IO subsystem, and then it will return from the system call, and of course it will end as IO is already complete, input data available, or output is completed. So the life cycle of an IO request is shorter if the answer for can already satisfy IO request is yes, but if no, it will still undergo many steps and it will be passed from one of course, for device driver, device controller, interrupt, handler, and the kernel I/O subsystem. Okay, next is we have streams. So stream, so it is a full duplex communication channel between a user level process and a device in UNIX System 5 and beyond. So a stream consists of stream head interfaces with the user process, driver end interfaces with the device, zero or more stream modules between them. So each module contains a read queue and a write queue. So they are always a pair. Then message passing is used to communicate between queues. Then flow control option to indicate available or busy. Asynchronous internally, synchronous where user process communicates with stream head. So this is an illustration of the stream's structure. So the user process, and then for the stream head, there's always a pair of read and write queue. So the direction of the write queue is of course, going to again to our another queue, write queue, and then it goes to the device while the read queue is going to the user process. Okay, next is we have performance. So I/O is a major factor in system performance. So how? So demand CPU to execute device driver, kernel I/O code, and then context switches due to interrupts, and then next is data copying and network traffic, especially stressful. So we have an example here of a remote login. So how it is illustrated for intercomputer communication. So for example, a user type username and password. So by means of typing, interrupt is already generated, and then interrupt received in the kernel. This is the kernel already. And then it will be of course handled by the interrupt handler. And then we have the device driver, and then the context switch, because of course the CPU um, will postpone its task and then will service the interrupt request. And then we have for the user process, the character is received, and then what will it do? It will send a character to the network adapter. So from the network adapter, it will send the packets to the other network adapter of the other computer. Then after it has sent the packet, it will return from the system call. And then the network adapter has already acquired the packet, so there is an interrupt generated. And then again, if it will be received from the kernel, and then it will be handled by the interrupt handler, and then of course the device driver, and then there's also a context switch, and then the network daemon. And then next is we have the packet received by the user process. So this is how it is, the remote login is illustrated. So remote login, you're going to access your computer, your computer by using another computer. So that is the remote login. Okay, next is we have improving performance. So to improve performance of I/O is we have to reduce the number of context switches, reduce data copying, reduce interrupts by using large transfers, smart controllers and polling, and use direct memory access, use smarter hardware devices, and then we have also to balance the CPU, memory, bus, and I/O performance for highest throughput, and then move user mode processes or daemons to kernel threads. So we have this device functionality progression. What if you have the programmers invented a new algorithm? Actually, it is easier to modify the application code. And then if the application code has improved its performance, then the changes can be reflected in the kernel code also. And then if it is okay, and then it can also be reflected in the device driver code, and then next is in the device controller code and the device code. So we have this arrows here, meaning, so for the device functionality progression for here, so up to device code, which is for the hardware, it is increased time in generations, and then also modifying it for performance, it is increased in efficiency, and of course it also increases in development cost, because this is it is harder to implement. So that's why for new algorithm, it will always start in the application code, and it also increased abstraction. And the only thing is for the application code is increased flexibility, because it's easier to modify than the kernel code, device driver code, the device controller code, and the device code. Okay, next is we have the illustration of the I/O performance of storage and network latency. So this shows the CPU and storage devices into two dimensions. We have the capacity and the network latency, of course. So next is we have of course, the capacity and latency of I/O operations. So added to this is a representation of networking latency to reveal the performance task of networking that is add to the I/O. So for example, for memory, so the operation is load and store. So we have the CPU caches and the DRAM and or the DIMM, and then we have the NVM. And then for storage, which is the operation is read and write, we have for the PCIe, the NVMe or the NVM for SSD. So this is the illustration here. Of course, for this example, for storage, the slowest, of course, is HDD. So, because it has a higher latency. And the fastest, of course, is the PCIe and the non-volatile memory. And then for here, for memory, so CPU caches are the fastest because they are relatively smaller than the NVM or the DRAM. Okay, so this ends our discussion on chapter 12. So all about input-output systems. So I hope that you've learned something with regards to the different I/O devices and how these I/O devices are handled and maintained by the computer system. So if you do have any questions, so please feel free to comment below. And please don't forget to subscribe to my YouTube channel. So again, thank you very much. Good day and always stay safe.